start from where we left off last time, and we were looking at perspective transformation. Basically, we were looking at the problem of finding the image point corresponding to a world point or a point in the real world when the camera axis and camera coordinates were not coincidental with the world coordinate axis. And what we found was we could write down our transformation to determine a point in the camera coordinate system CH. We had to multiply a number of transforms, the perspective transformation, the gimbal offset, the rotation which can be clubbed together, the pan and a tilt, and then the translation of the global axis to the gimbal center. All this has to be multiplied to the world homogeneous coordinates, right. One can write this all out. Each of the transformation is fairly simple, and finally one can say that x, that is a camera image plane x axis location of a point, will be given by the focal length of the lens times x minus x naught cosine of theta plus y minus y naught sine of theta minus divided by minus of x minus x naught sine theta sine alpha plus y minus y naught cosine theta sine alpha minus z minus z naught cosine of alpha r3 plus lambda. Okay, this determines, so given any global coordinates x, y and z, right, and the parameters which define the location of the coordinate frame of the camera with respect to the global coordinates, which basically is determined by the offset of the gimbal center x naught, y naught, z naught, the pan angle theta, the tilt angle alpha, and the offset of the gimbal, the image plane center with respect to the gimbal center, which is r1, r2, r3. So here r1 and r3 are appearing. Lambda, of course, is the focal length of the lens. Similarly, you can write down for the y coordinate, you will have lambda times minus capital X minus capital X0 sine of theta cosine of alpha plus y minus y naught of cos theta cos alpha plus z minus z naught of sine of alpha minus r2. This in the numerator, denominator remains the same. Okay, so this is the kind of relationship that you will get when we are looking at a camera which is not coincidental with the image plane axis. Okay, now let's illustrate that. So let's consider our global coordinates capital X, capital Y, capital Z. Let me imagine that there is a point 1 meter in the x direction, 1 meter in the y direction, and say 20 millimeters above the ground plane. So 1 meter, 1 meter and 0.2 meters. This point I want to know where this will appear if I had a camera which is mounted with the image plane with the axes So this is my x axis, y axis and small z axis. So, my camera is put with the image plane center along the global z axis, and I am looking at this point and I want to know where this will appear in the image plane. Of course, I will have to be given a few other things. I will have to be given what is the focal length lambda, let us say is 35 millimeters. Okay. I need to know what are the other parameters. So, x0, y0, both are 0, z0 is say 1 meter. So, this is also 1 meter. Okay. Now, what is the tilt and the pan angle here? We will have to see how much it is x axis and small x axis is rotated. So, if this is the plane that defines the, and so this is the angle that we are talking about, this is 135 degrees, and the other angle we are talking about is the x z direction versus the small z direction. So, we are talking about angle here. Okay, so that is also I have taken 135 degrees. So, we have pan angle theta is equal to 135 degrees and tilt alpha is equal to 135 degrees. All right. Now, we also need to know R1, R2 and R3. So, let us say R1 is equal to 0.3 0.03 meters, and R2 is equal to R3 is equal to 0.002 meters. So, this will now I have all the information. I will be able to compute where what this point W looks like in the camera coordinates, which will be somewhere on this plane, right. So, one plugs in the thing with all the simplification that we have here. So, one can reduce this to lambda times minus 0.03 divided by minus 1.53 plus lambda, okay, and y is likewise given as minus 0.42 divided by minus 1.53 plus lambda. And if you substitute the value of lambda, we get for lambda is equal to 0.035, it gives us x 0.7 millimeters and y equals to 9 millimeters. So, this is just to illustrate that once you have all the parameters, you can determine what the coordinate image point would be of a given scene, okay, which is what we are interested in. Okay. Now, one other way we can go from image point to the real world, we earlier when we looked at the inverse perspective transformation or imaging transformation, we found that there was some ambiguity. If you have an image point, you could not determine for sure what the coordinates of the external world point were, because everything in a so one way one gets around this problem is by looking at what is called stereo imaging. If you have, instead of one camera, if you have two cameras, then we can determine the z axis also, and that is what we will look at now. Supposing I have two cameras and I will only show the image planes of these two cameras. One, these are the two image planes with the axes these two axes are parallel. So, this is my say x1, y1, z1, this is z2, x2 and y2. Okay. Now, I have got two cameras, both are parallel, they are displaced from each other by some amount, say let us say b along the x direction, and let us define the global axis, global x, global y and global z to be coincidental with the first of the cameras, right. So, now of course, we have some focal point, I am assuming both the cameras are identical. So, we have some focal point, let us say the focal point was here and here, and let us take a let me take a image first and then correspondingly find. So, I have got this and I have got some image here. So, passing through here I get a, I look at a world point here w, small w, and I have one image C2 and I have one image C1 here, image point corresponding to this particular point, right. The idea is that if I know x1, y1 corresponding to this and x2, y2 corresponding to this, then I want to know where this particular point is in space, right. So, let us start out by looking at the first camera. Okay, for the first camera we have the two coordinates are coincidental, okay, coordinate systems coincidental. Therefore, we can write down, let us say for x1 coordinate as capital X 1 divided, I am sorry, I am looking at the capital X I am trying to determine x, small x1, okay, divided by lambda times lambda minus capital Z1. This is what we had determined earlier, this is small x by the way. Okay. Okay. Now, how do we find out the coordinate? We have some small x2 here, how do we relate this to the coordinate of this particular point in the global coordinates? Well, we have done much more complicated thing in the example and in the when we saw in general case. So, what we have is we have a displacement of this coordinate system with respect to the global coordinate system, that it is displaced by a amount b. So, in terms of what we had seen earlier, we have x naught is equal to minus b. If you refer to the what we have done so far, y naught, z naught are all 0, r1, r2, r3 are 0. So, we have a very simple case. What we can determine is that x2 x2, which is the coordinate of this with respect to this coordinate frame now, okay, which is nothing but x1 plus b, right, and this now simply can be written as x2 divided by lambda minus z2, right. Both these image planes are aligned along the x axis. So, then z1 is equal to z2, right, because whether I am that frame is the same distance z, and that let us say is equal to z. So, what I can do is now I can use this relationship, I can subtract one from the other to get a relationship, and I substitute for z1 and z2 equals to z. From all this I get that capital Z equals to lambda minus lambda b divided by x2 minus x1. Okay. Now, I can use this z into this expression to find out that x1 is in fact equal to x1 over lambda, okay, times lambda minus z. Z is this, which is lambda minus, so it becomes plus lambda b divided by x2 minus x1. Okay, so this cancels off, and then you will see that this lambda will cancel with that. So what will be left with is x1 times b divided by x2 minus x1, right. Similarly, I can find a global y1 coordinate as small y1 times b divided by x2 minus x1, and of course I have already found z here. So I have all the complete global location of the points known if I have two cameras instead of one camera. Okay. Okay. So next thing that I want to look at is basically the issue of camera calibration. What does camera calibration mean? It basically means that I want to determine the transformation matrix that I have talked about, which is the product of P times C times R times T. Now, if I compute it from the pan angle, the tilt angle, every error in that each of these quantities is going to lead to a error in the transformation matrix, right. So from time to time I will need to calibrate it by actually knowing some points in the world frame which are known coordinates, and looking at the image points and then trying to determine what this transformation matrix is, right. So fact that we have camera coordinate vector is equal to some P times C times R times T times the world homogeneous coordinate vector. So I can say that all this is collapsible into one single matrix, because each of these is a 4x4 matrix. So when I multiply it out, I get 4x4, and let's call that A. That is a transformation matrix which I am interested in. Now in general I can write, so if I am given some world coordinate point, okay, so that is x, y, z, 1, and I have this matrix here which is a 4x4 matrix, and it has some elements. I do not know what the elements are, so let me write them as, okay, even though you can't read each of the subscripts very well, you know what I am writing. So A31, A32, A33, A34, and finally A41, A42, A43, A44. I have got these 16 elements in this matrix. This is multiplied, and what I will get from this product is essentially some x times k, some y times k, some z times k, and k, which will correspond to the camera coordinates. So from this, if I want to determine what the camera coordinate is, I have to look at the fourth element in this vector and divide each of the other elements. So let us say this, what I will see in the camera is some CH1, CH2, CH3, and CH4, and I understand that if I want to get actually what the coordinate in the camera image plane is, I will simply get it by CH1 being divided by CH4, and similarly y will be equal to CH2 divided by CH4. Okay. Now let me multiply this right hand side out. So I will get CH1, which is nothing but x times CH4. Okay. So let me write the first row as x times CH4, that is equal to A11 times x plus A12 times y plus A13 times z plus A14, right. Similarly, I have y times CH4 is equal to the second row, which is A21 x plus A22 y plus A23 z plus A24. Okay, third row I am going to ignore, that is not significant. I will look at the fourth row though. So CH4 is given as A41 x plus A42 y, A43 z plus A44. Okay. So now what I can do is I can do some manipulation here. I can use the fourth equation, which is the third equation that I have written here, corresponding to the fourth row of the matrix equation, and I can substitute that in the first two equations to eliminate CH4. So I will have x and y relating to capital X, Y and Z through the coefficients that we have. Okay. So now let me do that. So what I will get is, first equation that I will get is, if I substitute for CH4 and take everything to the one side, so I get A11x, which I had before, plus A12y plus A13z, right, plus A14, and now I am taking the what was in the left side, which was x times CH4, and CH4 I am now substituting. So therefore I will get minus A14, sorry, yeah, A41, okay, let me write it here, minus A41 times x times small x, okay, minus A42 times small x times capital Y, minus A43 times small x times capital Z, minus A44 times small x equals to 0. Okay, all I have done is I had this equation here, so I am substituting for CH4 from here, right. So CH4 is dependent on A41, A42, A43, A44, and this gets multiplied by the small x, and I am taking it all to the right hand side, so I get this equation here. Okay, similarly I will get an equation for the second row, which is A21 times x plus A22 times y plus A23 times z plus A24 minus A41 times small y times x minus A42 times capital Y minus A43 times small y times capital Z minus A44 times small y equals to 0. Okay, so much for algebraic manipulation that we have been doing. What, just look at these equations now. I have two equations. How many unknowns are there? I do not know the coefficients of the matrix that I am trying to determine. So I do not know all these A11, A12, A13, A14, A41, A42, A43, A44, right. These are 8 plus 4, A21, A22, A23, A24. These are the unknowns for me. What I know is I will decide on a point in the global x, y and z coordinates. Not only that, I will decide a number of points, say supposing I have some well known points. So it could be part of a box that I have kept here now. in the view of the camera, right. I am able to see this corner, this corner, this corner, this corner, this corner, and this corner. So I can see 6 points in this. Size of this cube or rectangular parallelepiped will be known to me. So I know locations of each with respect to each other, right. I can also know the location of this whole box with respect to the global coordinate frame. So knowing this, I basically know x, y, z of 6 of these coordinates. I have 12 unknowns, I have 2 equations here. So if I write these equations corresponding to 6 points, right, then I will be able to solve for the unknown coefficients. So this is typically the way the calibration would be done. You will take some kind of a fixture or which has known dimensions, and the corner points can be identified easily in the image. It could be done automatically in using some kind of image processing that we will see further in the course. So we can basically find out the corner points, knowing those x, y, z coordinates and knowing the corresponding image coordinates. I can substitute them in these 2 equations. So 6 times 6 points times 2 equations, 12 equations I will get, and I have 12 unknowns. It is a linear solution problem of simultaneous equations. All right. So this is how cameras are generally calibrated. It could be done periodically, it could be done once in the beginning of the task and then next time when it is used. Okay. So now let us move on from what we have seen so far. Is we have seen that this is the image formation and transformation, the imaging geometry is what we have seen so far. Now what we will concentrate is that we have an image, which means we have a matrix with, okay, we have a matrix with discrete number of pixels. Each of these pixels has some intensity value. So my image is defined as, is written as x, y, some function of that which is the intensity. So this is the intensity at location x comma y, x being this, y being this. So if I look at some particular pixel here, then what is the intensity at this particular point? If I specify for all the image points, then that is my image, right. So now what we are going to do is we are going to look at how we process this information from the image. Okay, so we are going to look at now image processing. But before we look at image processing, we will look at some basic concepts. Some basic terminology and concepts. First thing is neighborhood of a point. Neighborhood of a pixel. So if I have a pixel here, there are some neighboring pixels. Okay, there are different types of neighbors I can define. So this is my pixel, say P. Then I have a neighboring pixel here, neighboring pixel here, neighboring pixel here, neighboring pixel here. So I can define these as 4 neighboring pixels, and these are called the 4 neighbors. Or 4 neighborhood. So in the point P, the 4 neighborhood of this point P is this one, this one, this one, and this one, right. So obviously if this had location x, y, then the 4 neighbors are going to be x minus 1 y, okay, which will give me this pixel. So just remember that I am keeping x axis here, y axis here. So x minus 1, this is x y, x minus 1 is this one, and y is this one. So this is the one that I am talking about. Then I have y minus 1, sorry, x and y minus 1, x and y minus 1. Then I have x and y plus 1 and plus 1 and y, which is this one. So these are the 4 neighbors. Now I can also have other type of neighborhood, which is the diagonal neighborhood. Okay, diagonal neighborhood, and this is called, this will be called D4, or sorry, N4, neighborhood 4 of P. This will be called neighborhood diagonal of P. Okay, and now diagonal neighborhood is basically these other 4 pixels which are not directly in the x direction or y direction, but which are displaced by x and y both, right. So the diagonal neighborhood is given by x minus 1 y minus 1, x plus 1 y minus 1, x minus 1 y plus 1, and x plus 1 y plus 1. Okay, this is the 4 diagonally neighbor elements or pixels, right. Together all these 8 neighbors is going to be called 8 neighbors, just like we called 4 neighbors. Neighborhood is the N4 and ND of a given pixel. Okay, this is just some definitions. This is what is commonly used. Okay, then we have the concept of connectivity. Okay, just like the neighborhood, we can define connectivity. Connectivity can be 4 connectivity, or 8 connectivity. But what it means is basically if I am given a pixel here, okay, and I have some neighborhood of this pixel. So supposing I am looking at 4 neighborhood, so I look at one of the 4 neighbors of this pixel, and then I look at the intensity value. If this has some intensity IP, okay, and this is say pixel Q, and this has some intensity IQ. If IP and IQ are same or nearly the same, then I may define this pixel to be connected to this pixel, right. Just imagine what we have. Basically we are talking about some image, right. So if in this image, say I have some line existing here. So let's keep it very simple. There is only one line here. So there are various pixels here, right. I am looking at the 4 neighbors. So basically this is the 4 neighbor of that, and they have the same intensity value or nearly the same intensity value. So what we will say is that these will be, something is connected if the corresponding neighboring pixel okay has intensity values belonging to a specified set. Okay, this of course will specified set will it may depend on the pixel under consideration. So, it will depend on x and y location in general. So, what I am saying is, supposing this is the pixel that I am considering right now, it has a intensity value of 67. If it is a gray image from 0 to 255, then it represents some amount of intensity or grayness here. Supposing this has 69, right, it is not identical, but I may define that given this as the intensity here, then I can define set V to include intensities 65, 66, 67, 68, 69, let us say. Then I am saying anything which is plus or minus 2 gray levels away from the pixel under consideration, I will consider it to be the same body, okay, because there are going to be some variation from pixel to pixel because of noise, because of variation of the source light, etc. So, there is going to be definitely some amount of variation, and that I am saying okay, I am going to define a set. So, if the pixel intensity belongs to that particular set, and if it is in the neighborhood, then I will say that these 2 points are connected, right. There is another concept of connectivity which is called mixed connectivity or M connectivity. Okay, in this case you have M connected region if firstly Q, which is the neighboring pixel, is in N4 of P, okay, or Q is in diagonal neighborhood of P and there is no common N4 of both P and Q. I think I need to illustrate this. Okay, so what I am saying is, let us consider part of a image, okay, and let me simplify things by saying that something is black or white rather than considering grays. So, it becomes simpler to see what has the same intensity value, whether something is a neighborhood or not. So, let me consider what one part of the image where you have this pixel is black, this pixel is black, and this pixel is black. Okay. Then if I am talking about M mixed connectivity, then if I consider this as my P pixel, okay, Pth pixel, then currently this is my Qth pixel, I am looking at this is in the 4 neighborhood. So, it satisfies the first condition, it has the same intensity, so they are connected. Now, if I come to this one here, it is in the 4 neighborhood, but does not have the same intensity, so it is not connected. Okay. If I look at this as a Q pixel, then this is in the diagonal neighborhood and it has the same intensity, okay, and further its 4 neighbors, which are these 4 neighbors, and its 4 neighbors, which are these 4 neighbors. So, the common 4 neighbors are this and this, and they do not have the same intensity, they do not belong to that region, right. So, then I will say that this is M connected, this is also M connected. Okay. Well, you could have simply said why not say 8 connected. So, let us look at another situation where this gets this is also has the same intensity value, right. This pixel is M connected, this pixel is M connected, and this pixel is M connected to this. So I have, this is my pixel, this is connected, but I will say that this is, I will not consider this connection, because it will not satisfy my second condition, that the common 4 neighbors of these 2 pixels that I am considering, okay, they have the same intensity value. So they are connected, therefore I will not connect this region here. So this is just to make sure that you do not have duplicate connections, because if you do not consider this type of neighboring or the connectivity, then in general you will connect this, you will connect this, you will also connect this, then there are duplicate connection, and when you run some of the algorithms, you will run into problems, because some duplicity has come and then values will not come out correct. So if in the first case when this was not black, so which was the case, if I show it again here, you have this and this and this, then you will have the connectivity that this is connected to this and this is connected to this. But when this is also present, then it is taken as connectivity being this way, okay. So this is our mixed connectivity that I have illustrated. Okay, then the next basic concept I want to deal with is concept of distance. Okay, now distances we are familiar with. So what we are familiar with is the Euclidean distance. Okay, let's denote this by dE, distance Euclidean. This of course we know is, supposing I take 2 pixels of interest, this is x y coordinates, this is another pixel somewhere, say this is u and v coordinates. So the distance between these 2 pixels is nothing but x minus u squared plus y minus v squared square root of that. Okay, this is how we define the Euclidean distance. Also we will take the positive square root of this. So if I consider distance, say from this black and white, it is very hard to show. Okay, so supposing this is my p pixel which I have already shown, and let us say my q pixel is this one. Now, so the Euclidean distance will be 1 unit, 2 units, 3 units, 4 units, 5 units along the y direction and 1 unit along the x direction. So in this particular example, okay, dE of between p and q is nothing but 5 squared plus 1 square root, that is square root of 26. Okay. Now another way we can define distances is if we look at the 4 neighborhood. Okay, so distance based on n4, right. So if I look at that distance, that will be what is also called city block distance. City block distance. So you imagine these to be streets and these pixels to be some buildings. So obviously you can't go through the building. So if you want to come from P to Q, then you have to go 1 block, 2 blocks, 3 blocks, 4 blocks, 5 blocks and 6 blocks, right. You have to travel 6 blocks. So this becomes, if I D4 between P and Q will be equal to 5 plus 1 will be the distance. All right. This way I can also define the chessboard distance, board distance, which can also be called D8 distance. Okay, this will be how many moves I have to make either along x direction or along y direction or along the diagonal direction. So here if I go 1, 2, 3, 4 and I can go from here to here. So I have the D8 distance between P and Q is only 5 units, right. Finally, let us also look at the M distance, which is the mixed mode distance criteria. So this time I will not paint them because then it becomes very difficult to see. So supposing I have, this is my P pixel and say this is my Q pixel, but now to find the distance it is not simply enough to look at this, because now I have to see whether they are connected or not. Only if they are M connected I can find the M distance. So it depends on what all, supposing I put the dot instead of filling it, so these are both black, then I have this one black, this one black, this one black, this one black, say I have, and rest of them are not black, which means the connectivity wise, if I look at my M connectivity, this is connected to this, this is connected to this, this is connected to this, this is not connected to this, right, because it gets connected through the neighborhood 4 connectivity as a preference. Then I have this connected and this connected. So therefore the distance here becomes 1 unit, 2 units, 3 units, 4 units and 5 units in this particular example. So what I have shown here as example, here I have the M distance or dm between P and Q is 5 units. Just notice that if this pixel was also belonging to this set, then the distance will reduce to only 2 units. Okay, so this, when this is Q, this is say R, if R is also connected, then dm will simply be only 2 units and not 5 units. Okay, so what we will do is, now we will stop here. Next time we will start looking at some of the steps that we require for processing the images, starting from pre-processing. Okay, thank you.